Hello, hi guys, good morning, welcome back to the next video. So in this video, we're going to see the problem number of sequences that satisfy the given sum condition no matter what. If you have solved this problem, no matter what, just watch this video because see, the logic would be for sure same. If you have solved it, logic would be for sure same, but the number of approaches to code that same thing will be different, and especially for the different languages also. Without further ado, let's start with this. And before that, if you just see that package, it came yesterday in the night, but I was tired, so I could not open it. But it is something related to the last Leetcode contest stream. So if you have watched it, you can just guess what would be inside that package. Just guess. If yes, you would guess right, then no worries. And also do let me know if you want unboxing of these kind of tech stuff in this channel, like just a normal unboxing, not a hi-fi unboxing. Before further ado, let's start this problem. It says that a number of sequences that satisfy the given sum condition. You are having an array of integers called as nums. Cool, no worries. And an integer called as a target. Cool. Nums and an integer called as a target. Return the number of non-empty subsequences of nums. Okay, it should have one or more element. Subsequence, which means any element in the order, any element. Number of subsequences. Remember this word, number. I am not concerned about this subsequence. I'm concerned about number of such subsequences. Number thing is, please remember, because it is very helpful. Cool. Number of subsequences, non-empty subsequences of num such that the sum of minimum and maximum element on it, basically the subsequences minimum and maximum element sum, it should be less than or equal to the target value. Remember, minimum and maximum element of that subsequence. I'm not concerned about the rest of the elements. I'm just concerned about the minimum and the maximum element. Since the answer will be pretty large, which means the number of subsequences can be pretty large, return it modulo 197. It is standard. Cool. First thing, I'm just concerned about the minimum and the maximum element of a part of an array, right? If we for now, let's forget, okay, it's a subsequence. Basically, subsequence says the elements needs to be ordered, right? But I'm not concerned about the subsequence itself. I'm just concerned about number of such subsequences, which I mean is if I have anything like that's 2, 3, 4, right? Let's say 1, 2, 1, 4, 2. Cool. A number of subsequences of this 1, 4, 2 and number of subsequences of 1, 2, 4. Are they both same or not? Same. Cool. So one thing I can for sure say that for number of subsequences, maybe the order might not be important. Maybe it is just an intuition which comes in our mind. We will verify it later, but it is first thoughts which comes in our mind. Okay, maybe the order might not be important, but let's see what we have to do. Okay, when it says, okay, just concern about the minimum and the maximum element. Now, while evaluating a subsequence, let's say if I choose some subsequence as 1, 2, 4, 6, 2, 5, 3, 1. Now, while evaluating a subsequence, let's say I choose this particular whole part. Now, I choose 2, 6, 5, 3. Now, isn't it very bad for me that I have to go on the entire array and see, okay, what is the minimum element? Minimum is this. I have to go on the entire array and see what is the maximum element, this. Maybe it can't be very easy for me if I just can choose, okay, the starting element is the minimum and the last is the maximum. As simple as that. So for that, what can come in handy for us is sorting, because I'm just concerned about the minimum and the maximum element. What if it can give me in the start and the end itself? So it is okay. One thing comes, okay, I just want minimum and maximum element. Maybe I can just sort it out. And I also saw earlier that sorting won't affect me as such, because I just want the number of such subsequences and number would remain same, because I just want minimum and the maximum element to, I'm just concerned about the minimum and maximum element of that subsequence. An element will for sure remain same. So maybe intuition one is that, okay, I can sort. Maybe it is a few thoughts which comes in person's mind while solving a problem. It may be wrong, it may be right. Cool. Now, it is the thought which came in while reading the problem itself. I have not even started to see the example yet. Now, let's see the example. 3, 5, 6, 7, and the target is 9. One thing I got to know that if you see the constraints, the number of elements are 1e5. So, you have to find the number of such subsequences in either O of n or O of n log n at max. You can't go beyond that. Which means if I just go the brute force way of finding the number of subsequences, let's say if I find number of all subsequences, which is 2 raised power n, then find the minimum maximum element. No worries. For let's say now I just sort it so I can find okay minimum maximum in just O of 1. Cool. And this to figure out okay how many such numbers, it will be 2 raised power n only, provided I sorted it initially. But it is still more, which means I have to find subsequences for, because see, one thing I for sure know, I have to go on to every element, which means I have to find what this element can contribute to me in number of subsequences such that the condition which follows, minimum and maximum sum is less than this target, it follows how much this element can contribute. Because one thing I for sure know, I have to go on to every element, which means O of n is for sure gone. So I have to find what this element, one element can contribute in number of subsequences in O of 1. I have to find okay what this 3 can contribute, what this 5 can contribute, what this 6 can contribute, what this 7 can contribute. I have to find this in O of 1 anyhow. Okay, now I've got to know one thing. For this array, when I'm iterating on this array, I land at 3. I have to find okay what this 3 can contribute in the number of subsequences. Okay, cool, no worries. For that, what I can do is for 3, okay, I'm standing at 3. Let's consider 3 as the minimum element itself. Now, what maximum element I can take in my subsequence? I can take, okay, if 3 is the minimum element, then I can, and 3 plus something, which means the maximum element, it should be less than or equal to 9. So, maximum element should be less than or equal to 9 minus 3. Maximum element should be less than or equal to 6. So, I think I got one thing for sure, okay, maximum element should be less than or equal to 6, which means in my subsequence, I know 3 will come for sure because it was said I want to choose a non-empty subsequence, and I considered, let's consider 3 as my minimum element or the one element, and let's choose the rest of this subsequence. Cool. I considered 3 as one of my element, maybe minimum, maybe not, but I considered one of my element. Now let's see, okay, what can be the number of subsequence. But if I consider one of the element, then it can come in minimum also, maximum also. So let's say okay, let's consider 3 as one of the minimum element itself, and let's try okay what all subsequences can be possible such that my other number is the maximum element. I can go okay, I found out that my m is less than or equal to 6, so it can be maximum element I can take in my subsequence. Now I just for sure know okay 3 is my one element I'm taking right now, and 6 it can be the maximum element I can take, which means more than 6 I cannot take. Less than 6, how many elements are there? Less than 6 elements are 2. Less than 6 elements are 2. So basically with the 3 I can take either 5 or 6, or no one else also, because I am also grabbing 3 as well, right? 3 I am for sure grabbing. For the other options 5 and 6 I have okay, I can grab it or not. My main condition, you saw what happened. My main condition was I need to grab an element less than or equal to 6. I'm just grabbing that. I'm just grabbing that element which is less than or equal to 6. Now for this I saw there are 2 elements which are less than or equal to 6. 3 I for sure grabbed, no worries. For that I have for 2 elements there are always 4 options. For one element you have 2 options, just grab it or just not grab it. 2 options. For the next element also you have 2 options, just grab it or just not grab it. So it is just two options. That is the reason I just say okay, no worries, you can just say that okay, for this grabbing 5 and 6 you have 4 options. So with this 3 number of subsequence I can form is actually 4. You can see one is with 3, one is 3 and 6, one is 3 and 5, one is 3, 5 and 6, and anyhow the maximum element is bounded by this particular 6 because it can't go beyond 6 because I always choose the numbers less than equal to 6, and for sure it's bounded by this 3 because I'm starting with this 3 itself. Now comes the interesting part. You saw what happened while I was choosing, okay, I want the number of elements less than 6. Won't it be good if I had already sorted my array so that I could get number of elements less than 6 very fast, maybe in O of 1 or maybe in O of log n? Because if it is sorted and you want the number of elements less than something, then you can just apply binary search and get, okay, number of elements less than something. That is, okay, one intuition which we thought of would actually help us, that we will just sort it just so that I can find number of elements less than a particular number in just O of 1. Cool. So basically, to get the maximum element, okay, one thing was I was standing at 3. I need to choose what element I can get. I can get a 6. For that, I just thought, okay, I will just sort it down so that I can just get it. Okay, what is the location of 6? And I'm standing here, so I can just grab this range for me, which means these two elements I can choose, okay, opt it or not opt it. So ultimately, I just need to find the position of this particular 6, which is nothing but I need to find the position of what is the maximum element I can get for this particular I right now. I considered 3. 3 is considered, which I'm considering right now as the minimum element. For this, I have two options. I can just use binary search or 2 pointers. Aryan, binary search looks fine, but binary search, like you said, okay, you want to find, okay, you know already you need to find a 6. So you said that it is sorted. I can find a 6 in my binary search because it is sorted. Finding a location of an element, it can be in O of log n. But how 2 pointers, Aryan? I could not understand it. Just see like this. If you have this number 3 and you have this number 6, let's say in the beginning, both the pointers of 3, 5, 6 and 7, in the beginning the pointers are I and j. Always 2 pointers is used because see, you have a limit that the sum of the nums of I plus nums of j, it should be less than or equal to target. This condition is satisfying. For sure, the range will always collapse. It will never go, okay, if our I is standing here. Now, I will say 3 plus 7, is it less than or equal to 9? So, I'll just decrease my j. Cool. Now, 6 plus 3, it is less than or equal to 9? Yeah, it is. Now, when 3 is evaluated, when number of subsequences possible for 3 are done, I will just increase the I. You remember one thing, your j never went forward because for sure I is increasing, and for 3 plus 6 it was the condition, okay, it was less than or equal to 9. Then for sure for 5 plus 6 it may or may not be, which means for 3 plus 7 where j was here, it was more than 9, right? If I increase this 3 to 5, it will for sure be more, right? So if I'm just decreasing it, which means now 3 plus 6 is at a brim of less than or equal to 9, is at a brim of 9. If I increase it, so for sure it will just increase. The left part will always increase, it can't decrease. That is the reason the number of subsequences possible, it can always just go. Thus I'm just using 2 pointers to find out, okay, how many number of numbers are there. Initially you will see I and j are here, so the numbers possible in this subsequences, I can just choose 3, 3, 5, 3, 6 and 3, 5, 6. It is how I'm choosing a subsequence like this. That is the reason I can also use a 2 pointer. I'll show when I'm just actually doing this 2 pointer approach that how it is being done. But now we just got to know that for every element, when we just choose, okay, I just choose right now I'm at index I. I'll just choose, okay, it is index I. Maximum element, it can be at index j. I will just choose, okay, number of elements, it can be, let's say number of elements which I can think of is 2, which is 5 and 6. So number of possible options are for me 4. For this element 3 right here, number of possible options, number of possible subsequences, it can be 4, which is 2 raised to power 2. This 2 right here is nothing but these number of elements, which are 2 elements. So if you just clearly look, it is nothing but if the index is I and the index is j, so it is nothing but j minus I. It will just nothing but 2 minus 0, which is nothing but 2. So basically j minus I returns number of elements here, right here. That is the reason I can just find, okay, for this particular index, the contribution of number of subsequences will be nothing but 2 raised to power j minus I. Now let's see what we got. The intuition, first intuition, we confirm it will sort. Why? Because for one index I want the maximum element j in O of 1 or O of log n such that I can find the number of subsequences possible for this particular I index in just O of 1 or O of log n. Okay, one thing I got for sure, no, that I will just sort it. Now next intuition which we had was the intuition right here, that to find this maximum element we just need a 2-pointer or a binary search approach, and that for sure will work because I just wanted our actually thing to work in O of 1 or O of log n. Thus to find this maximum element, or basically number of elements in the range from minimum to maximum, it can be done by 2-pointer or the binary search because the array is sorted because of the intuition one we had. Cool. Now comes the interesting part. Now you remember what we have to do. What we will simply do is we will just start our I and j. I'm just using a 2-pointer approach. You can also use a binary search approach, which means you will just start from this I. You know what is the maximum element, you know what is, you want 6, so you will just point it to 6 and will find, okay, number of elements in this range, which is j is pointing right now here. Now to find out the contribution of number of subsequences because of this I, it will be 2 raised to power j minus I, and it will be done. Same, you will just go on to the next element and then again do a binary search and so on and so forth. But the better way is not to do binary search again and again. You can just start from this pointer I and j and just keep on reducing the range, and as you keep on reducing the range I and j, you know, okay, this I and j is valid, so for this I, the range actually it can be 3 to 6, so the contribution will be 2 raised to power j minus I, and same, you will just keep on increasing your I and keep on decreasing your j, and for every of this element, at every I increase, you will just check, okay, what is the contribution of this I right now. So you can just easily do that. Let's see the code with this, how it is being done. First, to find the 2 raised to the power j minus I, as see, it is the indexes, it can go up to n, which is the length of the array. You just can't compute it by the normal method, because see, for every of your I movement, you have to compute this 2 raised to power j minus I. So for every of the I movement, which means every of the 2-pointer movement, because your I is moving, your j is moving, your I is moving, your j is moving. So for every of this movement, you need to compute 2 raised to the power I, or j minus I should say, which can be around O of n, which can be around n big. So if you just compute it linearly, then you are done, you are gone. Thus I told you that just watch this video. So basically, to compute our exponential number, which means a raised to the power n, we have a binary exponentiation which can compute this a raised to the power n in log n time. It is a very standard technique used to find exponentiation. You might have seen this in Fibonacci series also and other problems also, but it's a very standard problem to compute the exponents of a number. Thus you will see right here I am using a binary exponentiation. It is a very simple. It is nothing but if the number is odd, which means if your power right now is, let's say, 5, you will just simply, let's say you have a raised to the power 5. So what you will do is, let's say the result is right now 1, but a raised to the power 5 is there. So you will do a result is equals to whatsoever result is there, okay, 1 into just multiply by a once. So now the power will reduce by this number, 1 because you just multiplied 1 times only. But as soon as it becomes even, what you will do is, rather than just decreasing by 1 again, which means you have done a raised to power 3, which means 1 into a was already there, so like res is now a into a again, right? But rather than decreasing it by 1, you will just decrease it by 2, which means your 4, you have the power as 4, right? Now it will just decrease by 2, which means a will just, which means n, your n is power, n will become 4 by 2, which is 2. It just decreased by half. Rather than decreasing 1 1 1 1, as soon as it becomes even, just decreased by half, which means a becomes a, which was already a into a. That a, which was your this existing a, it becomes a. And mod p is just to make sure that okay, mod p is happening again and again. And that is how you will see your result. It was just like nothing but, sorry, your result, your just a is basically, see, it is one thing that result will be result into a in the odd operation only, but I'm just making sure, rather than just making multiplying by a, how about I just increase this a twice, which means you will see in the even time our result is not changing, but our a is becoming twice. And what will happen next time is, as okay, it becomes a 2, then it becomes, it is in the next iteration it's again even, so it will become a 1, so your again a is now a square, so it will again become a raised to power 4. Now in the next iteration, when n is 1, what will happen is it will just go on and multiply with this res, which was already a, so a into a raised to power 4, which is nothing but a raised to power 5. That is how you will get a raised to the power 5, where your 5 was gone. No worries, it was 4, it was decreased, I guess. Okay, it was 5, it was decreased to 4, and then we had this, when initially it was a, just make sure that it is at odd operations, I am just increasing my res into a. In the even operations, I am decreasing my n, which means n if n is even, so now I am power, the whole power which is even, I'm decreasing it by half, which actually in turn increase my base component. Base component is a, it is being increased, which means a into a. Next time will be, let's say it becomes a square, so it will be a square into a square. Next time it becomes a raised to power 4, so it will be a raised to power 4 into a raised to power 4. And as soon as again my odd power comes, this a raised to power 4, a raised to power 8, everything which is already my a has been computed, it will just go and multiply by res, which was already being computed for odd thing. That is how you will just get it, because you are just doing a half every time. Thus you are getting the computation in OF log n. If you not got it, just go and watch the binary exponentiation. But if you just go and try run this, you will just easily get it. It's actually very easy. Now binary exponentiation, I just took a bit time to actually explain you binary exponentiation, but it should not be this case. But yeah, let's see what can be done now. Now as we know that it is, we have to sort. Now to sort, we can use apply a 2-point approach or the bind search approach. Bind search we will not apply for sure, it's a higher computation power. 2-pointer we can easily apply, it's lesser, because bind search to do the same stuff, to find for I, to find the j, it is using O of log n time, while the 2-pointer will use O of 1 time. That's the reason I'm just using a 2-pointer approach. Now the standard 2-pointer approach which comes in people's mind, that see, one thing, firstly I'll just show you a bit long code, but it is more intuitive to write and think. Then I'll just move on to a shorter code, which is actually short to write, but it is more complex for many starter people if you just start off writing a 2-pointer thing. Now to write a 2-pointer, it is for sure good that you move your I, one step you move your I, and in the next step you move your j, while you can do the same thing parallelly also, which means if you just, here you will see, in the next step I will show you how you can make it parallel, but here I'm just showing, okay, in the one for loop you will say your I is only moving. Here in this for loop your I is only moving until your I is less than or equal to j. It is one condition, because I and j are moving like this, so I is moving, j is moving, so you should need to make sure that they should move until they don't overlap each other or basically surpass each other. In the next loop, I am just moving my j. I is fixed. Now I'm trying to move my j such that the condition is followed, which means nums of I plus nums of j. If it is more than my target, I need to reduce. If it is more, I need to reduce. As it becomes equal, I will just go and say, okay, I have landed on my j. I have my I initially because of the above for loop. I have my I. Because of the below for loop, I have my j. And it is just I is moving like this, j is moving like this. Because of above for loop, I is moving like this. Because of the below for loop, while loop, my j is moving backwards. Now, when my j is done, I should firstly make sure my j should be at least more than equal to I, because you will see the condition is I is less than equal to j and j minus minus. So if I and j are equal, then still my j will increase. So it can happen that my j surpasses I. So I'll just check, okay, if my j is less than more than equal to I, then firstly I'll just compute the power, because I just want, as I said, for this number right here, if my I was here, j was here, 0, 1, 2, the number of numbers right here which are impacting my particular I are 2, which is nothing but j minus I, 2 minus 0. So I need to compute 2 raised to the power j minus I. J minus I are these numbers, and every number has 2 options, grab it or not grab it. Now I will just grab it, raised to the power j minus I. Now with this, I will just add for every I. For every I, I'm just adding, okay, what this power can compute, what this power can contribute to my answer, and ultimately I can return the result. It is one option to code. Now, if I don't know binary exponentiation, still I can solve this problem in O of n log n. How? Firstly, the exact same thing. I just sorted the thing out. It's the exact same part. I am moving my I and I'm moving my j. Here it is the exact same part if my j is more than equal to I. Now the exact same part that I'm adding my power in my result. But the only thing now you will change is that I one thing for sure know. If I just don't know binary exponentiation, I can't solve this. I can't compute this power again and again. Which means I can't compute 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4 up till 2 raised to the power 1e5. I can't compute, because it will be to actually compute this, I need to go on like linearly, which is O of n. As it is already O of n, so inside this, if you compute this O of n, so it will not work. It will be O of n square, which won't work. Thus, you have to just pre-compute it. Now, how to compute 2 raised to the power 6? If I have 2 raised to the power 5, I just multiply that by 2. I can simply get a 2 raised to the power 6. So I will just keep on computing like this: 1, 2, 2 square, 2 cube, 2 raised to the power 4, 2 raised to the power 5. Which means at this value, I will just say, okay, what was the last value? Multiply that by 2 and get the current value. What is the last value? Multiply that by 2, get the current value. As simple as that. What I will do is, you will simply see. Firstly, I have this one because I will for sure start with 1. Then I will just grab what is the last value. Last value is nothing but 1. Multiply that by 2. Multiply that is nothing but a left shift. A left shift operation is much faster than a multiply operation. Although both are same. Although I can just write the same thing as pre dot back into 2. I can write the same thing as this. But a left shift is a faster operation because it's a binary operation. It's faster operation than a multiply by 2. Cool. I'll just grab it and I will just push it. Basically, I'm just trying to make this particular pre-computation like this. With this help, I can just grab, okay, the power of every element up till 2 raised to the power n. I will just grab all the elements and will be computed in this pre-array, which means 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and so on. I will just use that pre-computation of j minus I, which is nothing but 2 raised to the power j minus I, and will return this value in O of 1 time. That is the reason how I can actually optimize it. Now, as you saw, we are just moving our I forward and j backwards, right? So as I showed you that it looks a bit bigger code, but it is a more intuitive code to write. You move your I, you move your j, right? while many people write it much shorter, that I will just move my L and R, which means I and J, until they both are actually less than equal to them, which means while my L is less than equal to R, I'll just move my L and R basically both parallelly. And it was also the same thing which we were doing. We were moving until it was less than equal to. So basically it is converting this whole thing into a while loop, but it's a much shorter and looks cleaner. How? What we can do is, the condition was that, okay, move L, move R. Move R when? Move R when your condition, okay, the sum of L and R, if it is more than target, then only move your R. Same thing what we did. Move R, firstly, the condition I should be less than equal to J, which is actually the while loop. Move R, move J if it is more than equal to my target. Then you just moved your J. Now, if it is not the case, then just add that contribution of that 2 to the power R minus L in your result. As simple as that. Added the contribution in my result. As simple as that. And also increase your R, which L, which means in the next iteration, your I will increase. That is the same thing which we performed right here in this particular code part. If you just see this code part, exactly the same part of pre-computation, exactly sorting part. This part, it became more shorter. Thus, it's a 2-pointer approach, which is shorter one, but it's a bit hard to actually write in this way, and it's also hard to debug if it goes wrong. But in this case, it is easier to debug. Many people may understand this, but according to my experience of teaching, many people have got this method as much more faster and easier, because it's more intuitive to actually see, okay, here I is moving, here J is moving, here I is moving, here J is moving. Now I and J have reached. Now let's compute what I and J have to do, and let's move your I further. That is how you will do. You can do also like this, just have L is less than equal to R, or I is less than equal to J. I and J, L, R. LR looks more of binary search thing, but it's not a binary search, it's a 2-pointer approach. Cool. Complexity I have shown you already, but I will still show you that this part, which is binary exponentiation, it is log n part, which will happen. You will see that firstly sort it, so n log n. While doing this 2-pointer approach, I is moving like this, J is moving like this. Ultimately, it will just move O of n only. Here, while doing the here you will see, while doing this power thing, it is O of n log n. For this n loop is O of n log n, and this is to find O of result, it is O of 1. So ultimately it's O of n log n. This whole part, it is O of n log n, which means that complexity will be O of n log n for my sorting, and O of n log n for this particular loop, which is 2-pointer approach. Space is O of 1 because I'm not using any space. It is the interesting part. Many people will say that in C++ and Java, the space used will be O of n because they have to do pre-computation, but they don't know that in C++ and Java we have. In Python, we also have that we can compute very big exponent very easily, but in C++ Java we don't have, so we have to do a pre-computation part. We have to take that route, but it's not necessary. We take the pre-computation part. We can also use the binary exponentiation. Many people don't teach this part. Maybe they know, maybe they don't. While in the case of pre-computation, firstly you will just use your O of n time to actually pre-compute. Space will be also O of n because of this pre-computation. Log n part same as the previous part. This pointer 2-pointer approach, I and J for sure. Then to actually get this power, it's O of 1. It's also O of 1 to actually compute. It's entirely O of n, which was earlier O of n log n. It was earlier O of n log n. Now it is O of n because of this pre-computation of O of n. So ultimately the complexity will be for sorting O of n log n, for pre-computation O of n, for actually 2-pointer approach O of n. But space will also be for sure O of n because you are using the pre-computation part. Thus you will see that space is O of n. That is what you have. And just lastly, if you had used binary search in place of 2 pointers, which means here in this place, if you would have used a binary search to actually find the location of this particular J, so basically your log n part would also have come in picture. So it was O of 1, it was O of 1, it was O of n to actually move on to every element. So it would have been O of n log n. So So it would have been a O of n log n here. So basically a log n contribution, sorry, O of n log n here. So basically rather than n, it would have been O of n log n if you would have used a binary search. That is the reason I would not recommend to use a binary search to find your j here, because ultimately the complexity will be of O of n log n also. Here also it was O of n log n, here also it will be. Here also it was O of n log n, but it was n log n log n. It was earlier n log n, which is less than n log n plus n log n. But here it will be O of n log n plus n, which is more than the earlier approaches which we saw. That is the reason. Just not recommend I'll to use the binary search. That's the reason I'm not sure that approach also, but you can also use the binary search part. That is all. C++, Java and Python code is down below. Python code is actually faster than all the codes because I'm just using pre-computation in Python also. While Python can compute the power itself, but this pre-computation is actually faster than the inbuilt thing which the Python can compute. So you will see that it will be faster than the standard if you just access your 2 raised power j minus I by the function of Python. So yeah, that was all. I know the video has gone a bit long, so but I want to show you every approach, binary exponentiation, 2 pointers, binary search, everything. So yeah, it's all from me. I hope that you guys liked it. See you in the next video. Goodbye, take care.